This is the problems video for chapter 2. I will do example problems in each one of these sections, and then you are assigned to do the rest of the problems on your own. Follow along in the book so that you can read the problem as I am putting the information down. The first problem says express a length of 16.45 meters in centimeters and then in kilometers. So I have it set up here. I want you to set it up in this manner. This is using that dimensional analysis from our lecture notes. So if we start with what we were given, this is our given, 16.45 meters, and this is where we are going. So this is what we're finding. What we put in here is going to be that conversion factor that you just listened to in our notes, lecture notes, and that is going to be our known quantity. Now, do we know a connection between meters and centimeters? And we do. And if you look up above the board, you'll see the poster up there. There are 100 centimeters in 1 meter. Now the meters has to go down here because top and bottom units cancel. Now we're left with the units we're looking for. So you would take 16.45 times 100, and if you multiply that, you should get 1645. Excuse me, I keep stopping my recording. So 1645 centimeters. In this example, this is meters here again. We want to get to kilometers, so our conversion factor that we put in here will be the equivalence to meters to kilometers. There are 1,000 meters in 1 kilometer. So we have the meters cancels meters, top units cancel out bottom units, and you take 16.45 and divide by 1,000. So 16.45 divided by 1,000, do it on your calculators, and you would get 0.01645. And if you follow that moving the decimal rule, it also suits that rule as well. So your decimal is here, and you'd go 1, 2, 3, and there'd be a 0, and you'd have that 0.01645. Now that we've done the problems in this chapter, you do number 1 through 5 for this section as the section review at the bottom of page 40. So page 40, do 1 through 5. So in this problem with percent error, page 43, number 1 through 2, it says, what is the percentage error for a mass measurement of 17.7 grams given that the correct value is 21.2? So accepted, correct value, literature value, all of those words mean the same. Those are going to be this value right there. Okay, so let's put it into the problem, into the equation, and see what happens. So in this case, I get a negative 17% error putting the information in the problem, and that means that our value that we measured is actually low. That's what the negative sign is indicating, from what the correct value is. So you can have a negative percent error. That's just saying that you are low from what it should have been. So do number 2 on your own now, and then you can check your answers in the back of the book. This next portion on page 46 is working with significant figures, or sig figs. We're going to do most of number 1. I didn't have room for letter F. So we're going to look at number of significant figures. Follow the rules that are on page 45, and I will have a poster, which it's in the back of the room, you can see, posted on these. So we're going to work on these all year. 804.05. Underline, all non-zero digits are significant. Any zeros between significant figures are significant. So in this case, we have 5 significant digits. In this next example, underline all of the non-zeros, so those are all significant for sure. Any trailing zeros that are past the decimal, trailing, not this one isn't trailing, this one is a trailing past the decimal. That one is significant. These two, however, are not significant because they just tell us where that decimal is. They don't tell us that we measured this 1 to anything. It doesn't indicate a rounded number. This one tells us this is exactly 3, and then this 0 defines that 3. So we have 1, 4, so 1, 2, 3, 4. 1, 2, 3, and then this is between two non-zero digits, so 1, 2, 3, 4, 5, 6 significant digits there. In this example, our 1 and 2 are significant, and then zeros between significant digits are significant, so there are 4 in that one. This one, we have a 4, and then we have trailing zeros without a decimal. This one, there is only 1 significant digit. In this case, however, this decimal at the end makes this and this 0 all measured to exactly those zeros. So this is exactly all of those zeros, so that makes this 1, 2, 3, 4, 5 significant digits. That decimal at the end is what changes this number to being significant. Now do letter F and then do number 2, and you can check your answers in the back of the book. When you're doing significant figures and you're doing any multiplication or division, and then you have this number that gets spit out by your calculator, let's say you have, let me get an example out. Okay, so then in this example, I have 8.2 times 6.352, and then the calculator spits out this number. When you determine the significant figures for multiplication and division, here is my answer. In order to determine how many to keep, I look at my problem. This one has 2 significant digits. This one has 4. So I can only keep 2. You have to keep the least number from the problem. So in my answer would be 52. So that is how you do significant digits or significant figures after multiplication and division. When you do addition, so you have 4.2 added to 3, this would be 7.2, but this is to the ones position, so your answer can only be 7, not 7.2. So you have to go to where the least position is. So this would be the 3. Now do page 52, number 1 through 4. The answers are in the back of the book. Those are going to be pulling some of all of that information on significant digits and the density and conversions all together. Check the final answer for significant digits is what you're looking for in this as well. Okay, I will do number 1. So one of the first things I want you to do is read the problem, and then I want you to identify all of the information. So this is the information. They gave us a mass. I know that's a mass because it was in grams units. They gave us a density. I know that's a density because it's in grams per liter. And then they ask us to find the volume. Now I wrote liters back here because I know my answer, once my grams cancel out, will be liters according to what my density is in. So now I'm going to set the problem up on the next page. So my first step is I put my equation here, and then I'm going to plug the numbers where they belong. So this was the density, this was the mass, volume is my unknown. Now I'm going to manipulate by taking both sides times V, both sides times V. So once I multiply both sides times V, then I went ahead and further divided the number off of the V to get my variable alone. So then that will be 1.73 divided by 1.73 times 10 to the negative third divided by 0.17847, and that should leave us with our volume. So in our original problem we had 1, 2, 3, 4, 5, and in this one we had 1, 2, 3. So this one is going to define our answer, so 3 significant digits. My answer comes out to be 0.009693506, and then I added my units of liters there. So we don't want all of those digits, we only want to keep what is significant. So let's go back to our problem and figure out how many we can keep. So our final answer, and I will write it in scientific notation, will be 9.69 times 10 to the negative 123 liters. And that would be my final answer. Now do 2 through 4 on page 52, and hopefully we will all be on the same page. See you tomorrow.